Hi everyone. This time we're going to talk a little bit about simple electric circuits. Now this is just going to be a broad overview of the two basic types of circuits, which are series and parallel. Just as a reminder, electricity has to flow in a complete circle or circuit in order for it to work. If you interrupt that circuit anywhere, if it comes disconnected or you open a switch, it's not going to work. The two basic kinds of circuits, series and parallel, sort of work like this. In a series circuit, the charge comes out of one end of your power source, goes all the way around in one big circle, goes through one appliance, then through the next, and back to your power source. In a parallel circuit, it was described to me one time as rungs in a ladder. So the power comes out, goes through one rung, this appliance lights up or works, then the electricity can go through another rung, or the electricity can go through another rung. So there are multiple paths. Each one of these rungs are parallel to the other. So those are the two basic designs. As we look at these circuits, they are often drawn with symbols. There are multiple different things you can put in a circuit. We're going to stick to the very basics. The symbol for one chemical cell, you put multiple cells together for a battery. A bulb can often be, I always taught that you drew a bulb like this. Some people draw bulbs with an X. A motor, a switch, a simple switch can be like that indicating open, or like that indicating it is closed. A fuse fuses to prevent something from overheating, too much current going through a line. An ammeter, voltmeter, which we will talk about, a resistor, and a ground. Now, if you drew a circuit like this, so you actually have all of the constituent parts drawn out like a drawing, many of us are not great artists, and so it is easier and a little bit more compact to draw it using electrical symbols. In lab, when we start building circuits, we're definitely going to be using symbols, and you're going to need to know the basics just so you can interpret what you're being asked to build. Now, in a series circuit, there is just one path for the electricity to follow. The electricity goes through every single one of the appliances and then back to your power source. One of the criteria or properties of a series circuit is that if the circuit is broken anywhere, the entire circuit stops. This can be maddening if you're talking about Christmas tree lights. Some Christmas tree lights are wired in series. Now, if they're wired in series, one bulb goes out and the whole part of the string that happens to be wired in series with that one crazy bulb goes out. And I get frustrated when I deal with series Christmas tree lights, and I usually throw them in the garbage can. My husband has the patience to go through and fix them, but I don't. It can be really useful if you want a light switch that is in series with a bunch of outlets in your living room. Very often in a living room, there is not an overhead light. And so instead, there are a whole bunch of electrical outlets around the room. And there is a switch on the side of the room that when you turn that switch on or off, anything plugged into that switch is going to be attached. So you can have lamps, you can have all this lovely romantic mood lighting around the room, and the switch is in series with the outlets. You turn it on, all the lamps come on. You turn it off, all the lamps turn off. Many rooms, it's only the top or only the bottom plug that is in series with the outlet, so you can still have other things plugged in. In a series circuit, the current, if you put an amp meter or an ammeter in the circuit, the current is going to be the same everywhere. So if you had 3 amps of current, which is quite a bit of current, coming out of your power source, and you measured it at any point in that series circuit, that current would be exactly the same at every point. But the total voltage is going to be the sum of the voltage drops through each resistor. So let's say that you had a total of 9 volts. You had a 9-volt power supply or a 9-volt battery that you were using to power your circuit, and that each one of these resistors was equivalent. What would happen, it's kind of like 9 volts. Remember, this is electrical potential. It's kind of like your energy you've got to spend. So you've got 9 volts. So as the electricity goes through the first resistor, if all of these resistors are exactly the same, maybe 3 volts of electrical potential get used here, and there's a 3-volt drop. And then as it goes across the next resistor, there's another 3-volt drop. And then it goes through the next resistor, there's another 3-volt drop. And when it comes back to the battery or back to the power source, you're down to 0. So one side of the battery is 9 volts, the other side is 0 volts, because remember, this is just like potential energy or gravitational potential energy. Now, a parallel circuit, there are multiple paths for the electricity to follow. So if one part of the circuit is open, the others can still operate. So here's your power source. Here's one path for the electricity. Here's another path for the electricity. Here it's drawn in a sketch, and here it is drawn in using symbols. One path and the other path. This is typically how your house is going to be wired. Most of your house is going to be wired in parallel. Because think about it, if it was not wired in parallel. If your house was wired in series, can you imagine how wacky this would all be? If you had your kitchen appliances wired in series, your coffee pot, in order to run it, you would have to turn on the toaster, the stove, the microwave, and the lights. Because if one would go off, they would all go off. Well, that would just be goofy, and you don't want to do that. So it doesn't make any sense to wire your household in series. You want to be able to run the coffee pot, run the toaster independently if the others are running or not running. And that's why most household wiring is going to be parallel. Now, in a parallel circuit, the voltage drop is the same across each branch. So let's say your power supply is 120 volts like household current. So across this, it's going to be 120 volts. Across this resistor is 120 volts. And across this appliance, it's 120 volts. Why is this handy for household currents? It is very consistent for the appliances. For the appliances, it is all nice and predictable for the appliance manufacturers. But the total current is the sum of the occurrence in all of the branches. So let's say you have coming through your wire, let's say you have 3 amps of current, and your 3 amps come here. It's sort of like there are 1, 2, 3 paths that current can flow through. And maybe 1 amp goes through this channel, 1 amp goes through that channel, and 1 amp goes through that channel. If all of the resistors happen to be identical, the current comes back all to the same spot and returns. Because amperage is more like water flowing through a hose. It's not identical, but it gives you something visual to hang on to. And where voltage is a drop from one side to the other, like potential energy. Now, there are meters that we use to measure current and voltage, ammeters for current and voltmeters for voltage or electrical potential. When an ammeter is connected, it has to be put into the circuit. You have to break the circuit. You have to put the ammeter inside the circuit so that the current can flow through that ammeter. Ammeters usually have very low internal resistance because they don't want to mess with the current that they are measuring. Voltmeters can be placed across whatever they're measuring. So you just take a voltmeter and you put the probes on either side of a resistor to measure the voltage drop. Take a voltmeter, put the probes on either side of your power source to measure the voltage drop. Voltmeters have a tendency to have a very, very high internal resistance to avoid changing the circuit. Now, why would that matter? Because as current flows through here, the current is going to sit here and go, the current's going to go through the appliance or go through the voltmeter. If this has a really big resistance, current is going to take the path of least resistance. It doesn't just matter about you and me doing homework. It's the path of least resistance. It works for the electricity too. So most of the current is going to flow through here. A tiny amount of current is going to flow through here, just enough to register that voltage. And that way it's going to have a very small impact on what you read on your voltmeter. Most of the circuits in the world that you and I encounter are combination circuits. They're going to be a combination of a series and parallel bits. You talk about wiring everything from your cell phone to your iPad to a thermostat. There's a lot of parts to it, but they are made up of combinations of the basics. If you look at this more complex piece of circuitry, these two resistors are in series with each other. These two resistors are in parallel with each other. These two resistors are parallel, or these three resistors are parallel with each other. All of these little things right here, those are transistors, and we just didn't have a chance to talk about those at this point in time. Fuses and circuit breakers. These are safety features, and they are safety features that are built into everything from your home to your automobile. And they are designed to either melt, like simple old-fashioned fuses, or a circuit breaker is designed to switch the current off if things get too hot. If too high an amperage is going to go through a circuit, it can produce a lot of heat, because too much current makes a lot of heat, and you can risk electrical fires. And people who have lived a lot of years can probably name an acquaintance or someone they've known who has had an electrical fire. A lot of these can be prevented by using fuses, good circuit breakers, and making sure they are in good working order. Because once you break that circuit, the current will stop, and it will prevent the circuit from getting so hot that you risk those fires. So if you've got these in your home, make sure you always are replacing those fuses. Make sure if you've got an old-fashioned fuse box that you are taking care of those fuses. And all modern things up to code are using circuit breakers much better than the old fuse boxes were. All right, that will do it. See you next time. Bye-bye.